Yeah, thank you very much for inviting me to this very interesting workshop. And today I'm going to talk about three-layer cuprates. And this has been recently published in this reference. And these are my collaborators. Shinichiro Ideta is a main player. He has done a lot of work in high source synchrotron and also in UV source synchrotron. And sample has work on by Professor Watanabe and Professor Uchida's group, and theoretical support from TKD and Zong Ibo from National Tsinghua University and Tom Devros and his colleagues. So today I'm gonna focus on the multilayer cuprates, and so focus on the how TC maximum changes as a function of the layer. This has been long-standing problem that as a function of number of coupled plane, the TC usually increases with the increase in layer number, but decreases over 3 layers. So TC takes maximum at n equals 3. And so this problem has already been discussed 20 years ago, theoretically. And basically, my talk will give you a microscopic justification of this model, which deal with competition between superconductivity and which is in the multilayer cuprates, the interlayer tunneling enhance the superconducting transition temperature. But on the other hand, the antiferromagnetic order parameter also increases with increasing layer number, and they are coupled, and eventually this antiferromagnetic order parameter compete with superconductivity, and that's why we take the optimal condition at n equals 3. So this is our first RPS work on the 3-layer cuprates by Donlai and ZX group. And so they observed DUM superconducting gap and pseudo gap, and the corresponding to the highest TC maximum, the gap magnitude takes a maximum, become very large in the n equals 3. So several years after that, we identified the splitting of the frame surface into outer plane and the inner plane of the multilayer structures. And two frame surfaces, outer plane, both are gap behaves as a D wave, and inner plane is larger compared to outer plane, but finally near the anti-nodal region, this superconducting gap is taken over by a pseudo gap like this. And but outer plane, the superconducting gap defined by the slope of the nodal quasi-particle is already over standard magnitude, but at inner plane, the magnitude is even larger, as already mentioned this one. And we have plotted the superconducting gap defined by the nodal pairing gap and pseudo gap for single, double, and triple layer. And since we had only one for doping at that time, we plotted inner plane and outer plane on a different position, the horizontal axis, and construct a similar phase diagram or doping dependence of the pairing gap and pseudo gap. And pseudo gap both increases, but pseudo gap increases only moderately, but superconducting gap increases very strongly from single layer to double layer to triple layer. Now, very recently, the 5-6 layer cuprates has been studied, but this is before going to the RPS data. This view graph shows the NMR results. They found the antiferromagnetic ordering in the inner layer of the 5-layer compounds, and superconductivity and antiferromagnetic order compete. And actually, the antiferromagnetic order disappears only in heavily overdoped compound, but slightly overdoped and optimally doped. Still, there are antiferromagnetic. And because of the antiferromagnetic order, a recent report by Kondo and their co-workers found that the frame surface of inner 2 layers are so-called that those of folded frame surface of folded Briand zone, namely small hole pockets created by antiferromagnetic ordering. So, but we have studied the triple layer carefully again, and the triple layer, this effect of antiferromagnetic is much weaker, and overdoped, optimally doped, and are all superconducting. And there is antiferromagnetic order, but nail temperature is quite low. So we have studied many samples in this range, and looked at the frame surfaces. And as before, we observed the inner layer frame surface for the inner plane and the outer plane for all the dopings. But actually, inner layer, the doping is really so small, but we couldn't pin down the doping level because there is no antiferromagnetic hole pockets. So we extrapolate this region to an anti-node region where the pseudo gap completely obscure the frame surface. So this corresponding to the weakness of the antiferromagnetic watering. Now, these are typical spectra from node to anti-node, off-node, and superconducting gap is D-wave like, but above TC, still there are pseudo gap of similar magnitude. And this is, as already mentioned by Fabio, that pseudo gap, below TC, superconducting gap is D-wave like, but increases above the superconducting gap near antinodal region. There is a signature of pseudo gap. And but above TC, this nodal region collapse into a so-called Fermi arc, but pseudo gap region doesn't change so much. So this is these are data for many different doping from underdoped to overdoped, and as I mentioned earlier, for optimally doped sample, the overdose sample has a smaller gap than the inner plane. Because the scale is different, from different scale. And also, you can see that at above TC, the Fermi arc develops in the outer layer, but actually the inner layer of the underdose sample, you don't see a Fermi arc. Well, Fermi arc is very, very tiny. So let's look at closely this particular composition, the inner plane spectra. So these are the temperature dependence of the spectra from the below TC to above TC. And this D-wave-like behavior continues up to almost twice TC, and eventually the Fermi arc develops. So like most of other cuprates shows Fermi arc suddenly appears above TC, but in this inner plane of the under cuprates, the Fermi arc length remains very, very tiny until we reach twice the temperature of the TC. So this is a intensity plot. Also below TC, there is a gap in inner plane, and but this gap, actually symmetry, electron hole symmetric gap, persists up to twice TC, and eventually becomes gapless or pseudo gap-like behavior. So if we summarize the data, this part is the same as before, but this as we have a lot of more data points because of the many different samples, and these data are these points. The white circle, the square from inner plane. This is located in very low doping and very large energy gap or pseudo gap and pairing gap, nodal gap. And this region is from the outer plane, mainly outer plane, field circle from outer plane. And so if you plot those data in a single graph, this gap systematically increases with decreasing for doping. We also plot the pairing intensity, pairing temperature, above which the gap actually, superconducting gap actually collapse is this region. Still, the spectra looks like a D-wave superconductor. So we name this region as a nodal metal. So let me again show the previous reports on the 5-layer cuprates and our 3-layer cuprates. The difference is, as I emphasize again, this they show hole pockets, but we don't. The reason for we propose, we speculate that the reason for the difference is in the 3-layer cuprates, the pair tunneling or proximity effect on the inner plane comes from both sides of the inner plane. So proximate effect is very strong in the triple layer. So that's why the D-wave-like behavior is strong, even above TC or up to twice TC. On the other hand, in this 5-layer case, the central plane is not superconducting. So for this layer, proximate effect occurs from one side of this layer. So proximate effect is weak, and this inner plane, IP1, still antiferromagneticaally ordered, and the electron small hole pocket persists. And so this difference is maybe the reason why the TC max is suppressed beyond n equal 3, because the antiferromagnetism compete with the superconductivity, and finally TC drops. If I have a few minutes, let me briefly mention about the recent observation of the report by Xinjiang Zhou's group, that there are triple layer 3 frame surfaces has been observed by Xinjiang Zhou and their colleagues. And these are actually, we have studied this composition, but Xinjiang studied even higher doping level. Then they found 3 frame surface, alpha, beta, gamma. Actually, the highest one is almost 40% photo from frame surface area, and lowest one, the inner one, is only below 10%. So this data can be plotted on our phase diagram, and alpha, beta, gamma, overdoped, optimally doped, and underdoped from this data. And recently, we have studied even more heavily overdoped bismuth 2223 and found these 3 frame surface, 2-layer splitting, and 3 frame surface. So there, all the data looks consistently with decreasing concentration, and gap increases, and the 2-layer splitting and without 2-layer splitting may be related to the contact with a point below which we saw only 2 frame surface, and beyond this, there are 3 frame surfaces. So wrap up the summarize, and we have observed a very large nodal gap. Extrapolated value is exceed 100 millieV, the largest number in heavily underdoped inner plane, and above TC, this D-wave gap persists in some cases up to twice TC. And the reason for the TC max is highest in the N=3 is due to the because of the proximity effect from both sides of the inner plane, and which is very unique situation of the N=3 materials. And this explains why TC is highest in N=3. Thank you very much for your attention.
Thank you, Atsushi. Thank you so much for the very, very interesting talk on the multilayer systems. Questions, please. So let me maybe start with one, which is really on why is TC higher for N=3 versus 2? I mean, you explained that, then you were going to the 5-layer and showing there now you have, really the inner layers are very far away from the outer layer, the very large distribution in doping level, and many of them are really very underdoped. So our proposal, so then a question is microscopically, why is TC higher for the 3-layer than for the 2-layer system? Our proposal, as you know, we have also done work on this, was that perhaps the tri-layer is the best of the 2 worlds. You have, 2 outer layer, very overdoped, very high coherence, and then an inner layer, very underdoped, very strong pairing. And now you couple 2 superconductor, one with strong pairing, one with strong coherence, and that may lead to increased pairing in all of them, and eventually in higher TC. Is that sort of the same picture you're thinking of?
Yeah. That picture still survives. No argument against that. Yeah,
I see.
Totally, I agree with.
Which was sort of the idea pushed forward at one point by Steve Kivelson or so, and collaborators also, the coupling of these 2 systems. Okay, thank you. Thank you for that. Any other question? Yeah, Jumiao?
Yeah, maybe just a very naive question. So in LAPAS, can you tell which features are coming from the outer layers and which feature is
Yeah.
inner
Yeah,
layer?
we can.
Yeah.
Yeah. Sorry. Yeah, sure. We all actually in triple layer we maybe and double layer only one kind of
Yeah.
the
Right.
plane, but there is a bonding anti-bonding splitting. So we have two frame surfaces, and then in the case of triple layer, we have two kinds, and so and but due to hybridization between this, in principle, we can have three different frame surfaces. And so after hybridization, actually, it is not trivial, but before we observe the triple layer splitting, the inner layer and outer layer are okay. We under the assumption that the outer layer is more overdoped, more doped than inner plane. Then frame surface area different, so we can uniquely identify. But if our whole distribution is opposite, then this assignment will change. But I think everyone believes that the outer plane is more overdoped than inner plane.
Yeah.
I mean, yeah, go ahead.
If I could add, if you look at, certainly the on-site energies are different between the inner layer and the outer layer because of a different coordination.
Yeah.
So now if you look at the relative ratio of on-site energies and hopping parameters, what you may expect to be happening is that the inner layer really remains a pure state, while the other two are bonding, anti-bonding split. And as you go close to the zone boundary, you see that splitting. And indeed, that's actually what you find. So you do find that there are two Fermi surfaces which are degenerate at the nodal direction, and then they split at the zone boundary. And so these are the outer layers, while the inner layer now is separate and has no weight, basically, from the wave functions from the two other layers, and has a smaller volume.
Yeah.
So that is actually what DFT would tell you, and actually that's what you find.
I'm partially motivated also by the tri-layer Nicolaides. In our calculation, we see that the effect, some, like the quasi-particle renormalization, for example, for the outer layers and for the inner layer can be different. And obviously, the coupling between layers there is different. The z-square is very strongly coupled across layer, etc. But if one can make the assignment about that differentiates between the outer layers and the inner layer for that case, it might be very interesting. Yeah.
Here, I think you do it based on some knowledge of the density of a DFT band structure.
Right. Okay, thank you.
In the case of hybridization tests, we need to look at the DFT or other information.
Thank you.
If I may add, maybe in the work we have done on the tri-layer, we also do resonant X-ray, and we see charge order in resonant X-ray, and then we do it. When of course you don't know which layer. Is there a difference between inner layer and outer layer? Where is that charge order signal coming from? But then we do see in the photonic some anomaly in the dynamics, which is only there for the inner layer. So that's how now we relate the behavior of the inner layer as far as the photoemission to the charge order that we see in resonant X-ray. And so then we attribute the charge order to the inner layer, which is indeed then behaves as an underdog cuprate. But yeah, so
Yeah,
it needs some educated, interpretation of the data. It's not direct, It's
yeah, we did the rigs also
yeah,
on charge order, but we don't know which layer, probably inner layer,
I see.
but no experimental evidence.
Right. Well, our evidence was coming from a time-resolved experiment that you can do
Yeah,
both on the inner layer and the outer layers.
yeah.
And the inner layer shows an anomalous behavior, which then you can relate to a specific Q vector. And then you go
The
do resonance.
time resolved rigs.
No, time-resolved photo emission.
For the
And in the
okay.
dynamics, you see an anomaly that you
Yeah.
can relate to a specific Q vector. Then you do resonant elastic X-ray, say,
Yeah.
and then you see that at that Q vector, there is indeed signature of charge order.
Oh,
And so then you connect the two. And if it was for the outer layer, it would be a different Q vector. So then it all seems to make sense.
yeah. Q vector is different. Yeah.
Any other questions? If not, I think we're doing great. We are ending pretty much on time, even for the last session. So the whole workshop has been very well, timed and managed. So thank you again, Atsushi, and please join me in thanking all of the speakers of this session, but in fact, all of the speakers of the conference. And I'd like to give a last word to Chimiao, who has really led the organization of these events. Please.